Imagine you're standing in a dimly lit room, holding a heavy industrial rope. Attached to a solid brick wall, you give the rope a sharp flick, and a wave pulse travels straight toward the bricks. Watch closely at the moment of impact. The pulse doesn't return the way it arrived. It violently whips to the underside of the rope and travels backward, completely upside down. Why does hitting a flat surface force the wave into a total physical inversion? This precise mechanical reaction is governed by a rule in physics known as the boundary condition. To understand why the wave flips, we need to look at the exact physical constraints that the wall places on the rope itself. Look at this animation of a wave moving toward a fixed point. We call this the incident wave. That black dot represents a rigid boundary. Because it is completely immovable, the displacement of the string at that exact location must always equal 0. We can describe this incoming pulse mathematically. Y sub I equals A sine of kx minus omega t. In this equation, A represents the amplitude or peak height of the wave, and omega represents the angular frequency. To ensure the string stays perfectly still at the wall, the math demands a reflected wave that is the exact geometric opposite of the incoming one. As the blue incident wave and the red reflected wave meet at the boundary, their amplitudes add together and perfectly cancel each other out to 0. This geometric shift is called a phase reversal of pi radians, or 180 degrees. It is the only physical way to satisfy the wall's absolute requirement for 0 motion. We can also explain this reflection through Newton's third law of motion. As the incoming wave arrives, it exerts an upward force on the wall. Because every action has an equal and opposite reaction, the wall pulls back down on the string with the exact same amount of force. That downward snap physically generates the inverted returning wave. Now, let's look at an open boundary setup. The string is tied to a lightweight ring that slides freely up and down a vertical rod. When the wave hits this time, the ring simply rides the pulse upward. There is no rigid surface pulling back against it, so the returning pulse remains entirely upright. The equation for this reflection is y sub r equals a sine of kx plus omega t. Notice the negative sign is gone. The shape of a reflected wave is ultimately a mechanical record of the force the boundary was or wasn't able to exert. Let's put both systems side by side. On the left, our fixed wall. On the right, our sliding ring. We send a pulse down both strings at the exact same time. They hit their respective boundaries and freeze. At the rigid boundary, the wave undergoes a phase reversal of exactly pi. At the open boundary, the wave reflects with 0 phase change. Ultimately, this simple physical boundary condition dictates exactly how all of this wave energy bounces back into the world.